Hello friends, so in this video we are going to solve one of the numerical based on the vapor compression refrigeration cycle. We are going to see one special case from the vapor compression refrigeration cycle, that is the wet compression. And in this wet compression we are going to see the three different cases. So let's get started. So the question is, a refrigeration system at what point these values are there. So in this image you can see, so at 40 degrees centigrade this HF, this is from the table, it is 148.631. you can see here it is 148.631. same thing is mentioned here. Likewise, at minus 40 degrees centigrade enthalpy of vapor is given as 374, so that we are calling it as Hg. So on this line we are considering as enthalpy of gas, so that's why the suffix symbol is Hg, and on this line it is enthalpy of liquid, that's why the specific symbol is HF. Similarly, we can get for the entropy as well. So entropy is also given at specific temperatures. So entropy at minus 40 degrees centigrade, entropy of liquid is given at this one. Same thing is mentioned over here. Likewise, at minus 40 degrees centigrade, entropy of vapor is 1.76. It is given over here. Likewise, at higher temperature also, entropy of liquid is 1.3339, and that is mentioned over here. And entropy of vapor at higher temperature is given, and that is mentioned here. Remember, these entropies are at these points. Okay. Now with the help of this knowledge, we try to draw vapor compression cycle. Always first we try to draw the vapor compression cycle. See, the first case, dryness fraction is given as 0.9. So the point 1 is inside the dome, but we are not sure about the point number 2, whether the point number 2 is inside the dome, whether it is on saturated vapor line, or whether it is on outside of this dome. So to check this point number 2, we need to see the entropy at point number 1. So we want to mark the location of point number 2. So that is our first step, to check the location of point 2. So for that we'll see the entropy at point number 1. So as per the theory, we know that S1 that is equal to S2. So by using this, we'll try to find out what is the entropy at point number 2, and with the help of that we'll try to see what is the location of point number 2. Okay, so S1 that we can find out as, since the point number 1 is inside the dome, so it is SF1 plus X1 into SG1 minus SF1. Now this point number 1 lies at minus 40 degrees centigrade temperature. So whatever the SF values are there, SF and Hg values related to the minus 40 degrees centigrade, that you need to put here. So if you do this calculation, you will get entropy at point number 1 is 1.667788. You can write up to 4 decimal places. Now you need to compare this value of entropy at point number 1 with respect to entropy of vapor at higher degree temperature. So entropy at vapor at 70 degree temperature is 1.6965. So we can see that since the entropy at point number 1 is less than Sg at higher degree temperature, that is 70 degrees centigrade, therefore this point number 2 is inside the dome. That means this point number 2 is also in wet region. Okay, so point number 2 I will mark over here, since this point number 2 is also inside the dome. So with the help of this we can complete our diagram. So this is 1 to 2, that is compression process, then 2 to 3 constant pressure condensation process, then 3 to 4 is expansion process, and 4 to 1, that is evaporation process. Okay, so this completes our vapor compression cycle on TS diagram. Okay, similarly you can draw the pH diagram as well. I will not draw the pH diagram. Then we know as per the theory that S1 that is also equal to S2. So value of S2 is also equal to 1.667788. Then with the help of this we can find out what is the dryness fraction at point number 2, that is X2. X2 we can find out. So with the help of this X2 only we can find out the enthalpy at point number 2. X2 we can find out by considering S2 as SF2 plus X2 Sg2 minus SF. So I'll put these values. So if you do this calculation, you are getting the X2 as 0.9208. So almost we can consider it is 0.92. So by using this, we can find out enthalpy at point number 2. So X2 we got as 0.92. So by using this, we can find out the S2. S2 is HF2 plus X2 into Hg2 minus HF2. Just put the values. So if you do this calculation, you will get the H2 as 419.0865. You can write up to 4 decimal places, kilojoule per kg. So this is the enthalpy at point number 2. Similarly, you can find out enthalpy at point number 1, and since this point number 1 is also inside the dome and X1 is given in the question as 0.9, so H1 we can find out as HF1 plus X1 into Hg1 minus HF1. So just put the values. So if you do this calculation, you are getting the H1 as 351.5243 kilojoule per kg. And the enthalpy at point number 3, since the point number 3 lies on saturated liquid line, so directly we are getting from the table the value of H3, that is 304.515 kilojoule per kg. Okay, you can see here. And as per the theory, we know that H3 that is also equal to H4. So all the enthalpy at 4 points we got. So this is the enthalpy at point number 1, enthalpy at point number 2, then enthalpy at point number 3, and enthalpy at point number 4. Same thing. Then as per the question, we want to find out what is the refrigerating effect for this case. So that is nothing but mass flow rate of the refrigerant into H1 minus H4. So we can put the values. Mass flow rate is 1. H1 we got as 351.5243, and H4 it is 304.515. So refrigerating effect we are getting almost 47 kilowatt. Then work input we can find out. It is mass flow rate of the refrigerant into H2 minus H1. The work input is 67.5622 kilowatt. The COP we can find out as refrigerating effect upon work input. Corresponding values we need to put, like refrigerating effect is 47 and work input is 67.5622. So ultimately we are getting COP as 0.66 6957. So this is the COP for the first case when x1 is 0.9. Now let's try to solve for second case. Now for the second case, x1 is given as 0.9297. So with the help of this, our point number 1 is again fixed. It is inside the dome only. But point number 2 we don't know. Again we need to check by considering the entropy at point number 1. So S1 that is equal to SF1 plus X1 G1 minus SF1. So it is 1.6965 kilojoule per kg Kelvin. Now if you see the entropy at point number 1, it is exactly same as entropy of vapor at 70 degrees centigrade. So as per our theory, S1 that is equal to S2, and S2 we can see by using this table, it directly lies, this point number 2 directly lies on saturated vapor line. That means this is your point number 2. So we can join this point number 1 and 2. So once you got this point number 2, it is very easy to find out the enthalpies. So H1 we can find out as H1 we are getting as 358.2197 kilojoule per kg. H2 we can directly get since the point number 2 lies on saturated vapor line at 70 degrees centigrade. So H2 we are directly getting from the table as 428.941 kilojoule per kg. Then point number 3 is also on a saturated liquid line. So that value also we can get. So at 70 degrees centigrade, enthalpy of liquid, that is enthalpy at point number 3. So it is 304.515 kilojoule per kg, and that is also equal to enthalpy at point number 4. So refrigerating effect we can find out as mass flow rate of the refrigerant into H1 minus H4. So just we'll put the values. So refrigerating effect we are getting as 53.7048 kilojoule per kg. Similarly, you can find out the work input. So mass flow rate of the refrigerant into H2 minus H1. So it is getting 70.7213 kilojoule per kg. So COP we can find out very easily. It is the refrigerating effect upon work input. So this value we are getting as 0.7594. So this is for the case 2. That is when the dryness fraction is 0.9297. Now let's talk about the third case. That is case C. Dryness fraction at the entry to the compressor is 0.95. So again to check the point number 2, we need to see the entropy at point number 1. So if you do this calculation, you are getting the entropy at point number 1 as 1.7161 kilojoule per kg Kelvin. Now with respect to the entropy at point number 1, you see the entropy at higher temperature, entropy of vapor at higher temperature. So that is 1.6965. So S1 entropy at entry to the compressor is more than entropy of vapor at 70 degrees centigrade. So therefore, point number 2 lies in superheated region. Okay, that means the point number 2 is somewhere, we can say, outside of this dome. So it may be somewhere here. So let's complete this diagram. We try to see what is the temperature at point number 2. Because we don't know what is the temperature at point number 2, it is very difficult to find out enthalpy of at point number 2 without knowing the temperature. So first we'll find out what is the temperature at point number 2, and then we'll find out the enthalpy at point number 2. And let us consider this point as 2 dash. So S1 that is also equal to S2, and since the point number 2 it is in superheated region, so we can write like this. It is Sg2 plus Cpv into ln of T2 divided by T2 dash. So by using this, we can find out what is the temperature at point number 2. So S1, that is also equal to S2, that we have got, that is 1.7161. Sg2, that is nothing but entropy at point number 2 dash, and that value is 1.6965. Cpv, it is given for this vapor, and this value is 1.605. Then ln, that means log to the base e. T2 we don't know, actually we want to find out the T2, but T2 dash we have to consider in Kelvin, that is 70 plus 273. So if we solve this, we are getting like 0.01221, that is equal to ln T2 divided by 70 plus 273. Don't forget to write this bracket. So this is nothing but e raised to 0.01221, that is equal to T2 divided by 70 plus 273. So if we solve, getting T2 as 347.213 Kelvin. So this is the temperature at point number 2 in terms of Kelvin. By using this, we'll try to find out enthalpy at point number 2. So H2 we can find out as H2 is equal to Hg2 plus Cpv into T2 minus T2 dash. So Hg2, enthalpy of vapor at temperature 70 degrees centigrade. So enthalpy at point number 2 as it is 430.887 in terms of kilojoule per kg. So enthalpy at point number 2 we got. Enthalpy at point number 1 we can calculate. So enthalpy at point number 1, H1, it is equal to HF1 plus X1 Hg1 minus HF1, since the point number 1 is inside the dome. If you solve this, you are getting the value as 362.796 kilojoule per kg. Then enthalpy at point number 3, that is also equal to enthalpy at point number 4, 304.515. H2 we have already calculated, so that value is. So we can find out the refrigerating effect. If we solve this, you are getting 58.28 kilo. Now work input we can find out as mass flow rate of the refrigerant into H2 minus H1. Let's put the values. So if you calculate this value here, it is getting around 68.091 kilowatt. So this is work input. So with the help of this knowledge, we can find out the COP for this case. It is a refrigerating effect upon work input. Just put these values. We are getting the COP for this case as 0.8559. This is for the case 3. That is when X1 at the dryness fraction at the entry to the compressor is 0.95. So that's all from this video. I hope you understood the special case of vapor compression cycle as a wet compression. Please hit the like button. If you have any problems, please comment to this video, share it and subscribe to the channel. Thank you.